Okay, so today we're going to do the second half of 2.3. Once again, depending on the book you're using, this might also be like 2.4 and 2.5 if you're using the Briggs book. So we'll just get it to match with the homework, or you should just kind of get it to match with the idea of using limit laws. So what you want to do is you want to write down, pause the video and write down these first four. I'll go over these and then I'm going to go over the next four, okay? Okay, so the first limit law says the limit as x approaches a of f of x plus or minus g of x is equal to the limit as x approaches a of f of x plus or minus g of x, a limit as x approaches a. What this is basically saying is the limit of the sum is the same as the sum of the limit. So you can split a limit through addition or subtraction. It's not really called, you're not distributing the limit, but what you are allowed to do is take the limit term by term, okay? And we're going to practice some of these in after we go through all these. So this one says the limit as x approaches a of c of f of, or c times f of x. This is basically saying if you have a constant times a function, you can pull that constant out and then take the limit of the function by itself, okay, and then multiply by c when you're done, whatever that constant is. This is the product of f of x and g of x. So what you're allowed to do is you're allowed to split the limit of a product into the product of two limits or three limits or four, however many you need. So once again, you can split the limit through multiplication. The fourth one says you can split the limit through division. As long as the limit of g of x does not equal 0, you're good. So now here's these next five. Pause the video, write these down. Okay, so this one says the limit of f of x to some power of n. You're allowed to then just take the limit of f of x, and then whatever you get for that answer, move it to the power of n, or take it to the power of n. N must be a positive integer, meaning, 0, 1, 2, 3, 4, 5, so on and so on. Or I guess not 0, 1, 2, but 1, 2, 3, 4, 5. So then the limit of a constant is just the constant. Number 7, the limit as x approaches a of x is just a, which makes sense. Because if you want to know the height as x approaches a and you're just working with a line, well, then it'll be the height of that line at that point. The limit as x approaches a of x to the n is worth a to the n. And again, I think you're starting to feel like in these two, you're kind of just plugging in a in for x. And we're going to talk about that at the end here. These next two, the limit of the nth root of x is equal to the nth root of a. Again, we're just kind of plugging in a, but a must be a positive integer. And also a must be an even, if n is even, then we have to worry about a being a positive number so we don't get imaginary or complex solutions or complex values. The limit as x approaches a here at number 10 of the nth root of f of x behaves very similar to the previous one. You're allowed to take the limit of f of x as x approaches a, and then just take the nth root of it. Again, same as above, and when n is a positive integer, and f of x has to be greater than 0 if n is even. Now here's a big one. This is a huge one right here. Okay, so it says for polynomials and rational functions, we have the limit as x approaches a of f of x is equal to f of a. So this is very powerful because that means that if you're dealing with a polynomial or a rational function, you are allowed to simply plug a in, evaluate at a, okay? And that's because polynomials are smooth and continuous everywhere, and rational functions are continuous everywhere on their domain. So for rational functions, you still can't just plug in a if it's one of its vertical asymptotes or if there's something else going on there. But again, that's kind of with all these limits is, for the most part, you're allowed to evaluate at a, as long as it's not breaking any rules of math, like dividing by 0 or something like that. Well, then you can't use some of these. You have to find another way around it, okay? So let's try a problem, okay? So it says, and again, in these first few, I'm going to do it like a really slow, long, drawn-out way. And then I'm just going to show you, well, it's a rational function, so we can do this. So let's say evaluate limit as x approaches -1 of 3x over x squared plus 3. So what I'm going to do is I'm going to try to break it down into a bunch of limit laws. So the first thing I'm going to do is I'm going to notice it's a quotient. So I'm going to rewrite this as the limit of the quotient is equivalent to the quotient of the limits. So I'm going to say as x approaches -1 of 3x divided by the limit as x approaches -1 of x squared plus 3, right? Now, technically, that top one the numerator is 3 times x, so that's a constant. So I can take 3 out and do the limit as x approaches -1 of x divided by, and now this one I can split because this is two different terms. I can do the limit as x approaches -1 of x squared plus the limit as x approaches -1 of 3. And now this will become 3 times -1 all over. Now this, I could do it again, but I don't want to, but I could technically then take this power right here, but it's kind of becoming overkill at this point. So what I'm just gonna do is I'm gonna say -1 squared plus 3, right? So that's using the limit of a constant is just a constant. So we end up with -3 over 4, and that would be our limit. Okay. Now, what I could have done from the very beginning is I could have just said alternative is I could have said this is a rational function. And right here it says for polynomials and rational functions, we have the limit as x approaches a of f of x is equal to f of a. Okay, so alternate method. I could have just used that and said the limit as x approaches -1 of 3x over x squared plus 3 is equal to 3 times -1 all over -1 squared plus 3, which is -3 over 4. And I was allowed to do this because it says right here that if it's a rational function or a polynomial, we're allowed to just evaluate it at the given value, which was -1. So we get -3/4. Okay. Now let's take a look at another one. So evaluate. Let me do this. Limit as x approaches 2. I don't know why I keep doing that. X approaches 2 of x squared minus 4 all over x minus 2. So now if I try to plug 2 in, I say, oh, this is a rational function, I end up getting 0 over 0, and that's not good. So we can't do that. So what we do instead, because 0 over 0 is indeterminate, we don't actually know what the value is. We have more work to do. Whenever you run into 0 over 0, this is called indeterminate form. Okay, and that means we have more work to do. So when we get to L'Hopital's rule, I'll show you how that works with indeterminate form. So for now, we're going to have to use algebra or manipulation or something like that to find the correct answer. Well, in this case, we'll use algebra. This is factoring. So this is actually the limit as x approaches 2 of x plus 2 times x minus 2 all over x minus 2. So now we can cancel and cancel. And we end up with the limit as x approaches 2 of x plus 2, which equals 4. And we're done. And that's all there is to it. Okay, so we were able to use factoring as a method. Okay, so factoring is one, or let's say factoring is one technique used to help find limits, because it works especially well with rational functions. A lot of times rational functions have factoring. We can do some cleanup on those. Okay. All right, so let me take a look at another one. So basically what 2.3 is, it's kind of like unlocking you now. It's saying, okay, now you have all these rules. Now let's see what we can do. So notice here, I did it really slow. I broke it down piece by piece, but then I'd rather do it this fast way. So that's what we want to kind of graduate to. We want to do it the quicker way so we don't have to break everything down, but never forget that you have this method that, or I shouldn't say this method, but all these limit laws at your disposal where you are able to kind of break limits down and do them piece by piece. They'll often come up in harder problems when the limit's too hard to do overall. You want to come back and do a little piece of the limit, and then it'll get you started. But whenever we can, we try to do it the faster way. So let's say we have evaluate the limit as h approaches 0 of 2 over 7 plus h minus 2 over 7 all over h. So once again, I encourage you guys, whenever you're being asked to do limits, try to plug the limit in and see what you get. In this case, if I plug the limit in, I end up getting, once again, 0 over 0, which we cannot currently do. We don't have the tools to deal with 0 over 0. So that means we normally use algebra. So we're going to use some algebraic techniques to try to clean this one up. Well, the thing is we notice that the denominator is, just h, and we already have a problem there. So the numerator is something that we're going to try to deal with that hopefully will do some kind of canceling with the denominator. We're not exactly sure. Let's just see what happens. But in order to do anything, we need the numerator to be a one single fraction. So this is a complex fraction. So what we're going to do is we're going to say, well, this needs a 7 plus h, and this denominator needs a 7, and this multiplies by 7. So what I basically did was I just made common denominators. So now we're going to and don't forget to keep writing the limit. You cannot, how do I say this? You must always write the limit until you've actually used the limit as h approaches 0 or as x approaches 2 or whatever it is. So as long as you haven't taken the limit yet, you have to keep rewriting it. So we end up with 14 minus 2 times 7 plus h all over 7 times 7 plus h, right? Divided by h. So I wrote it sideways so I can look at it a little bit better. So now I'm going to have the limit as h approaches 0, and this will be 14 minus 14 will be 0, so we'll end up with negative 2h in the numerator, and the denominator will stay 7 times 7 plus h. But now this is times 1 over h, right? Because division is the same as multiplying by the reciprocal. Now I'm able to cancel. I'm going to cancel this h with this h, okay? And that's going to leave me with the limit as h approaches 0 of, not the 1, negative 2 over 7 times 7 plus h. Now we can finally take the limit because plugging in h will not result in division by 0. So now when I plug in h, I get negative 2 over 49. And notice I finally was able to stop writing the limit, but not before then. I was still writing the limit here, here, and here. So you must continue to write the limit as part of the notation that you need in calculus, okay? So please continue to write it, even though you're doing your homework online, or many of you are doing your homework online. Please continue to write the limits, even if I'm not necessarily seeing your work. Okay, on exams, I will be, looking to make sure you're writing everything correctly. Okay, now let's talk about dealing with absolute values. In general, for me, I feel like absolute values in calculus always seem to cause a little bit of trouble. So we always have to be a little bit careful whenever absolute values become involved. So dealing with absolute values. Okay. So when you're dealing with an absolute value in general, to turn an absolute value into a piecewise function is what we're going to do. So we are going to turn an absolute value into a piecewise. Okay, so this will be our normal technique. So technique part 1 is we will determine the values where f of x is positive and negative. And then step 2, we're going to create a piecewise. So we're going to take those values and we're going to create a piecewise for the absolute value. And this will be f of x for x values where f of x is greater than 0, and negative f of x for x values where f of x is less than 0, okay, or negative. Okay, so it's a little bit more of a process. So what we're going to do is we're going to try this example. We're going to evaluate the limit as x approaches 3 of the absolute value of x minus 3 all over x minus 3. Okay, so the first thing we're going to do is we're going to determine the values where it is positive and negative. So I'm only going to look at the absolute value of x minus 3. That's what I'm worried about right now. Because remember, that only deals with the absolute value. So the divided by x minus 3, we're not going to deal with just yet. So for the absolute value of x minus 3, I know that this will, let me see here, determine the values where f of x is positive and negative. So this means for positive, x minus 3 is positive when x is greater, x is greater than 3, okay? And x minus 3 is negative for x less than 3, right? Because if I plug in 2.9, this becomes negative, but if I plug in 3.5, this becomes positive, okay? X minus 3 becomes positive. So I have my kind of turning point, my window, so to speak, of when it's positive and when it's negative. So now what I can do is I can say the absolute value of x minus 3 is equal, and then I'm going to build my piecewise. So I have x minus 3 for when x is greater than 3, right? X minus 3 for when x is, and so all I'm doing is this right here, guys. I'm just using what I showed you in the previous step. And then we have x minus 3, right? It says use negative x minus 3, so I'm going to put a negative sign in front, okay? I'm just going to put a negative there. And this is for when x is less than 3. And again, I'm just following the steps that I put forth, okay? Now the problem is, oops, you know what, let me write this a little bit better. I'm going to need some space. So we're going to do our piecewise, and we're going to say x minus 3, x is greater than 3. And we're going to say x minus 3 negative for x less than 3. Okay, so now here's the catch. Notice the original problem is divided by x minus 3, and I don't have that. So what I'm going to do is I'm going to divide this by x minus 3, but then that means I have to divide this by x minus 3 and this by x minus 3. So that turns out to give me this new piecewise function that looks even cleaner, which would be 1 comma x greater than 3, and this would be negative 1 comma x less than 3. So all I did was notice that these now cancel and become 1, and these cancel and become 1, and one's positive 1 and one's negative 1, okay? Now they want to know the limit as x approaches 3, right? So I'm going to take the, remember I told you guys that when you're dealing with piecewise, you normally have to do a left hand and a right hand limit. So I'm going to do the limit as x approaches 3 from the left of f of x, or you know what, I'll write it out just so you guys can see it. Absolute value of x minus 3 over x minus 3. Well, from the left, let's see, what value is to the left? Well, this is to the right of 3, and this is to the left of 3, so I use negative 1. Okay, then I'm going to do the limit as x approaches 3 from the right of absolute value of x minus 3 over x minus 3. But that is from the right of 3, that would be this guy here now, right? So from the right of 3, we would use positive 1. So then this means that the limit as x approaches 3 of the absolute value of x minus 3 over x minus 3 is equal to d n e. Remember, if the left and the right hand limits do not line up at that value, the limit does not exist. The limit exists from the left, the limit exists from the right, but they're not the same limit, so we say does not exist. Okay, so that's how you can deal with absolute values. I think there's like maybe 1 or 2 in the homework. Okay, so let's look at a couple theorems real quick. So if f of x is less than or equal to g of x, okay, near x equals a, except possibly at a, and the limit as x approaches a of f of x and the limit as x approaches a of g of x exist, meaning they're not d and e, okay, then limit as, or d and e or infinity in this case, limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Okay, so what they're saying is if you have two functions, f of x and g of x, and f of x is always less than or equal to g of x near x equals to a, and the two limits exist, then the limit of f of x as x approaches a will always be less than or equal to the limit as x approaches a of g of x. The only weird exception, I guess, would be infinity, but I guess you could have less than or equal to still, but normally that's kind of, that doesn't come up as often, okay? So now here's a really big one. This one's extremely important. This one's kind of cool. This is a new way that some of you can look at math, the squeeze theorem. Okay, so the squeeze theorem is really cool because it allows you to solve problems without actually solving the problem themselves. You bound the problem in such a way that it has nowhere else to hide, and the only answer is the only answer is the last answer not eliminated. So it's if f of x is less than or equal to g of x, and g of x is less than or equal to h of x near x equals a, and then, except possibly at x equals a, and limit as x approaches a of f of x equals the limit as x approaches a of h of x, and they both equal some L, then the limit as x approaches a of g of x must also equal L. So basically what this is saying is that if this function is smaller than this function or equal to, and then this function is smaller than or equal to this function, then you can say if the limit of f of x equals the limit of h of x, if they are the same value and g of x is in between them, then the limit of g of x must also be that same value, right? So this is squeezing g of x in between f of x and h of x. So that's why it's called the squeeze theorem. Okay. All right. So let's try one of these. So I think I may have already talked to you guys about this, but I'll say evaluate. The limit as x approaches 0 of x squared sine of 1 over x. And by the way, when you guys are doing these problems, you can't just say the answer is 0 because the squeeze theorem. You have to actually show how you did it. You can't just say the answer is 0 because I remember from the homework that the answer was always 0. A lot of squeeze theorem problems are 0. They do result in the answer being 0, but that won't always be the case. So you actually have to show some kind of work. So the problem is with limit as x approaches 0 of x squared sine of 1 over x, the problem with this problem is you cannot directly plug 0 in. You cannot plug 0 in because you would have division by 0. Now you could say, well, 0 squared is going to be 0 times sine will be 0. Yeah, that's probably true, but I need some kind of explanation. So what we're going to do is we're going to bound sine of 1 over x. Now from your trig class or your pre-calculus class, you remember that the sine of any function or sine of any argument will be between -1 and 1, okay? So the sine of 1 over x is between -1 and 1, okay? So then what I'm going to do is I'm going to multiply this by x squared, right? So I can get sine, or x squared times sine of 1 over x. So now I have negative x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. Well, then what I'm going to do is I'm going to take the limit of each piece of this compound inequality, limit as x approaches 0, right? So now I have this. So basically what I'm doing is I'm building this problem from scratch, okay? I'm taking this problem and I'm building it from scratch. So we have the limit as x approaches 0 of each one of these pieces of this compound inequality. So now what's the limit of negative x squared as x approaches 0? Well, that'll be 0. I don't know this limit. If I did, wouldn't I have done it from the very beginning? Because this is the original problem, right? So this is the original problem that we're dealing with, x squared sine of 1 over x. I still don't know how to do that. And then I know that this limit over here is 0. Now notice what we're now saying is that, oh, and it's important to note, my inequalities always are staying lined up, right? I'm not changing the inequality. It's still less than or equal to and less than or equal to. So here's the thing. What does this have to be worth? Well, I don't know exactly what it's worth just yet, but I know that it has to be greater than or equal to 0. And I know that it also at the same time must be less than or equal to 0. Well, what's the only number that's greater than or equal to 0 and less than or equal to 0? Well, that's 0 itself. So we get to say the limit as x approaches 0 of x squared sine of 1 over x equals 0. And then you always follow it up by squeeze theorem. So the squeeze theorem it has your back, okay, by squeeze theorem. So it says if you got a problem with this, go look up the squeeze theorem and you can figure it out. But I showed my work. I did everything I needed to show you how I built the problem from scratch. Remember, I started with a simple sine bound. I just said this fact I know. So now would this work with cosine? Yes, it would absolutely work with cosine, but it would not work with tangent because tangent is bounded between negative infinity and positive infinity in terms of its range. Okay, so that wouldn't help for tangent, but for sine and cosine, a lot of times you run into these squeeze theorem problems, okay? So that's the squeeze theorem. Very important tool. We'll use that throughout the class. And not only is it important, but it's also a new way to think. You notice I found the answer to this, but I never actually did anything to this problem. I did something over here and over here, but I never actually did the limit as x approaches 0 of x squared sine of 1 over x. So this is a way that you start seeing that math can attack problems from the side, from a different angle than you thought was possible. That's why I love the squeeze theorem so much. It kind of opens your mind to what are the possibilities with higher levels of math and bounding and everything like that. So it's a really powerful concept to adapt, or I should say to acquire. So, you know, definitely make sure you understand it. It doesn't work for everything. It's for certain things that have bounds on it and things that we can easily bound. We like to use the squeeze theorem. Okay, so let's take a look at another one. Okay, so let's see here. Yeah, let's try this one. So we got another one I want to try. Okay, so let's evaluate. And it says the limit as x approaches 16 of x minus 16 over the square root of x minus 4. So once again, if we plug in 16, we would notice that we would get 0 over 0, which we can't do yet. That's something that's indeterminate form, and we don't have the tools for that just yet. We'll get to that in a different part. I think it's in chapter 4.4. But until then, we'll hold off on L'Hopital's. So those of you that already know how to do L'Hopital's, you can't use that for these problems. You have to wait till I show you how to do it in 4.4. So we have this. Then it says limit as x approaches 16. Okay, so what I'm going to do then is I'm going to try to think. I have the limit as x approaches 16 of x minus 16 over square root of x minus 4. Now I can't just plug in 16 because I'll get 0 over 0. So I remember from pre-calc, we had to rationalize denominators sometimes. So I'm going to try to rationalize this denominator, and I'm going to get the square root of x plus 4. So remember, you use the conjugate, okay? So we're going to use the conjugate in order to clean this up. So this will now become the limit as x approaches 16. And again, I haven't used the limit yet. I'm just doing a bunch of rewrites. And I'm not going to FOIL this out. I'm hoping something will clean up. So I'm just going to write x plus 4 all over. Now this will become x minus 16. What do you know? This cancels with this. And now I'm left with the limit as x approaches 16 of the square root of x plus 4, which is actually equal to 8. Yep, because this plugs 16 in, we get the square root of 16 is 4, 4 plus 4 is 8. So I can use conjugates, okay? So far, so in summary, some of our techniques that we have factoring. That can help with limits. What else do we have? What else did I use? Common denominators. We also have squeeze theorem. We have conjugates. usually for irrational functions. Okay, so whenever there's a square root in it or a cube root, well, cube root's a little bit harder, but square roots normally our kind of go-to move is conjugates. A lot of times with sine and cosine, our go-to move will be the squeeze theorem if it can't be solved quickly or evaluated quickly. Common denominators, most of the time that's with rational functions where they don't have the same denominator, or we use factoring with rational functions as well. Now, we also know that we have tables and graphs work really well. Okay, tables and graphs, but from now on, we will use, or I shouldn't say from now on, but we will use the techniques on the left. So we would much prefer to be using this, or this. I don't want to use tables or graphs very often. It's important that you associate tables and graphs with limits. And it's also important that you associate factoring and these other algebraic techniques with limits as a whole. So as a whole complete thing, you want to use all of these. But in general, in terms of work and what I'd like to see on exams, is I want to see the factoring, common denominator, squeeze theorem, or conjugates in your work. I don't want you to just draw a table for every single problem and just say, oh, here's the answer. I won't give full credit for that. Maybe I'll give a little bit, but in general, no. A lot of them you could put on your graphing calculator and you could just see the height and say, oh, that's the limit. I won't take that either. In general, you have to use these techniques on the side. Okay, every once in a while, they'll still obviously ask you to use a graph or use a table, but if they don't say, then I want to use these, okay? All right, you guys, that's going to do it for this video. Hopefully that gives you enough to get started on the homework. Thanks for watching.